All right, little practice. Go. Take the derivative. Nadia, how many functions? 3. How many chains? 2 chains? Good. Nadia, I forgot to ask you a question. Which function's on the outside? What's the outer layer of the onion?
The square.
Good. 3 for 3. Well done. All right.
I put those in parentheses though.
Except that should be a 1. Okay. Yes. No. No. Your last chain will be the derivative of that, so that should just be that without the cosine and the 2 in there. There you go. Now your business. Okay, so as Nadia mentioned, there are 3 functions there. The outermost function is a squared function. So if nothing else, you should be able to take the derivative of a squared function. It doesn't matter what the function is inside. Taking the derivative of a squared function, you bring the 2 down, reduce the power by 1 of this thing. Whoops. X cubed minus 4x. Okay. That's the original derivative. Then we have 2 chains, which is the next function in the layer of the onion. Cosine. So you take the derivative of cosine. What's the derivative of cosine? Negative sine of that stuff. This is bad math. Yes?
Yes.
This is good math.
Yes.
Or move the minus sign out in front if you'd like. That's 1 chain. I know I'm not done yet because Nadia told me I needed to chain twice. I've only chained once. Therefore, I lost an X here somewhere. There you go. Now I'm done. Now, do we care about simplifying? No. Could you simplify that? Yes. Is it relevant? No. And how are you going to simplify that? Well, like I said, you move the minus sign out in front of the 2. You distribute the 2 to the 3x squared minus 4. You can't really combine the cosine and sine without getting into some weird double angle formulas, which we're not going to do. So you're done. Okay? Questions? Good. That should be old hat for you now. Today, we're going to learn something called implicit differentiation. It's another tool that you can use to take derivatives, and it solves a simple question for us. Okay. Let's suppose I asked you to take the derivative of that. How would you do it?
Minus 4.
Y.
Get y by itself.
Get y by itself, correct. Get y by itself, then you have the function y equals negative 2x plus 4. Take the derivative of that. Boom, you're done. Okay, great. But what happens if you can't solve for y? Then you need to be able to find the derivative using something called implicit differentiation. Okay, and then today, please, make sure you know the difference between those three things. It drives me crazy. Okay. There, and there. Yes?
Yep.
Good. All right, so here we go. Before you start writing down, I'm going to tell you that you can make a choice. When you're doing implicit differentiation, do you want to use the notation dy dx, or do you want to use the notation y prime? Because they're the same thing. And you'll see as I work through the problem, some people like the dy dx better because it's easier to see. Some people like the y prime better because it's easier to write. I will say that when you do the y prime, you have to be careful that you don't misinterpret a y for a y prime. That doesn't make a lot of sense, but it will when you see me start doing these problems. Okay, now, if you're going to use the dy dx, let's talk about what does dy dx mean? The derivative of y with respect to the variable of x. Okay, it's a fancy way of saying the derivative. What is this? The derivative of x with respect to x. What's dx over dx? 1. Okay, that will become relevant if you choose to use that notation. And again, none of this makes any sense until you see me dive into the problem. Okay, so look at this equation, and you'll notice that is almost impossible to solve for y. If there's a way, I don't know what it is. And the energy that I would spend trying to get y by itself in order to use the tools we've used would not be worth it. So hence we have this thing called implicit differentiation. There's one thing you need to remember when you do implicit differentiation, and that is anytime you take the derivative with respect to y, you need to stick on a y prime or a dy dx, because remember those two things are the same. In fact, I'm going to put a little note up here. Dy dx is the same thing as y prime. Okay? So what does that mean? Okay, I take the derivative of y cubed. What's the derivative of anything to the third power? Say again? Who's talking?
Oh, Maria.
Maria, okay. I can't tell. We're back to the old days when I can't tell who's talking because you have math on. I understand. Take the derivative of this. You get 3y squared. But I took the derivative with respect to y. Therefore, I need a dy dx. I'm going to do the first one as dy dx just to show you what it looks like. Okay. Derivative of y squared. 2y, but I took the derivative with respect to y, so I need a dy dx. Minus the derivative of 5y is just negative 5 dy dx. Whoops. What's the derivative of x squared? 2x. Now you can think of this two different ways. You can, and I'm going to give you both options so that you can choose one that works better for you. I understand after doing this a while that I'm taking the derivative of with respect to x, so therefore there's nothing to add on to that. However, if you want to, you can add on a dx over dx. But that makes no sense because dx over dx is the same thing as 1, so I'm not going to bother. The single most common mistake when working with implicit differentiation is the following. What's the derivative of negative 4? 0. Okay? My opinion is that implicit differentiation is pretty easy. What makes the process difficult is I haven't found the derivative yet. I have to solve for the derivative. So what does that look like? dy dx times the quantity 3y squared plus 2y minus 5 is equal to 2x. Move the 2x to the other side. Anything with a dy dx stays on the left. I factor out a dy dx. Last but not least, I divide. Done. That little simplifying process is what's going to cause problems for you. Most of you will do it just fine with implicit differentiation. Question in the back.
Might be dumb.
It's not dumb.
Why can't you?
Well, it might be, so never mind. Go ahead.
Why can't you just take the derivative of x with respect to y? Because that's easy.
You can, but that changes the entire problem. You can take the derivative of anything with respect to anything else. It just changes what the variable is. Okay, so in other words, let's suppose I have t is equal to a times b. I can ask you, what is dt dA? Okay, I could ask you, what is dt dB? I could ask you, what is dt dQ? Okay. So, what is dt dA? That means, what is the derivative of t where a is my variable? So the answer here would just be b. Think of the a's as x's. If I did dt dB, the answer would be a. If I did dt dQ, I would get 0, correct, because these are all constants then, no variables in the problem, and the derivative of a constant is 0. Okay? So by saying y prime, we're implying that y prime is the same thing as dy dx. Okay? You will see some weird problems when we get into some trig stuff where you're taking something like dy d theta, where theta is your variable. Okay? Problems. We good? Yeah.
How would it look if we did it without an annotation? Or are we just doing that for a different problem?
I'll show you in a second.
Okay.
I'm going to do the next part of this. If you've looked ahead, you'll see what the next slide says. What if I want the second derivative? Okay. So this is what I had as an answer. And now I'll do this in terms of y prime just to show you what it looks like. Again, I prefer y prime, but if you want to use dy dx, you can. Okay, here we go. Y double prime is equal to, you want a quotient rule or a product rule with a chain rule? A quotient rule, good, okay. 3y squared plus 2y minus 5 on the bottom and square it. Bring that up on top. 3y squared plus 2y minus 5 times the derivative of the numerator. But the numerator only has x's in it, so I just get 2. Minus, big honkin' bracket, the top, times the derivative of the denominator, which is, 6y, y prime, plus 2y prime, close parentheses, close bracket. Where did the 5 go? Disappears, it's constant. Now this is kind of nice because I have the y prime, the y double prime isolated, so I don't have to do much else. except for one small thing. What's y prime?
2x.
Yeah, that monstrosity up there. Okay, so if in the future, if you're asked to find the second derivative here, you're going to have to plug in for y prime and simplify. However, more than likely, the problem would say something like, what is the value of the second derivative when x equals blah, 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 and y equals blah, blah, blah. Then you would just plug and chug. Very seldomly are you going to ask to take a monstrosity like this, and then take this beast, put it in there for y prime, and put it in there for y prime. And then simplify. Because eventually we're going to have two major rules. One rule is no negative exponents. The other rule is no fractions within fractions. That comes later. And you can see if I plug in y prime there, I'm going to get fractions within fractions. We'll talk later, or we'll refresh your memory later on how to get rid of fractions within fractions. Okay. So, does that answer your question, Allison? That's what it looks like when you use y prime. Again, I like the y prime, so I think it's easier, but you know that's what makes it such a great country. Put the bar right on. Determine the slope of the tangent of the graph of that thing at 3, 1. I'm going to keep the simplifying to a minimum here because I know that I'm going to plug in 3 for x and y for 1 to answer the question. And I didn't ask you for the equation of the tangent line, I just asked you for the slope. So I'm going to find the derivative, and that's it, I'm done. Okay, here we go. Let's use black. I get 6 times x squared plus y squared times 2x plus 2y, y prime, equals, uh-oh, product rule, 100y plus 100x, y prime. All right, so look at that for a second and make sure you understand where each of those little tidbits came from. The reason I didn't do this as a plain derivative problem is because you can see, hopefully you can appreciate the difficulty of having to solve that for y prime. I'm not going to do that. I'm just going to plug in 3 and plug in 1, and whatever happens, happens. 6 times 9 plus 1 times 6 plus 2y prime is equal to 100 plus 300 y prime. I would argue that that's a lot easier to simplify. Let's see. Let's do this. That can go away with that and that. See what I did there? What's the matter? Did I screw up somewhere?
No, I'm just confused.
Oh, okay, good. As long as I didn't screw up, that's good.
So, could you explain how you got the 100y plus 100x?
Okay, so I did this product rule as considering that the first term and that the second term. So I took the derivative of the red, which is just 100, times the blue. Then I did the red times the derivative of the blue. The derivative of y is 1, but I took the derivative of y, so I have to take a y prime on there.
Okay, thank you.
Okay? Good. We good so far? All right, let me finish this. 36 plus 12y prime is equal to 10 plus 30y prime. Therefore, 26 is equal to 18y prime, so y prime is equal to 13/9. I hope I did my math right. You don't have to simplify it that way. You could take 9 plus 1 is 10 times 6 is 60, distribute the 60 to each of the terms and get 360 plus 120 y prime equals 100 plus 300 y prime. Solve it that way, that's okay. Regardless of how you attack it, you should get 13/9. And I'm done. Now, if the problem said what's the equation of the tangent line, then you have the slope, you have the point. Go crazy with that, use it in point slope law. How will you know when to use implicit differentiation? 2 ways. Number 1, the problem will specifically tell you, use implicit differentiation to find blah, blah, blah. Or number 2, you will not be able to solve for y. If you get a problem that involves both x and y, I would take 3 seconds and ask yourself, can I solve for y here? Because if you can, it would make your life a lot easier.
Whoa,
And this,
Who sees that moving?
that's trippy. Yeah.
Who does not see that moving? Interesting.
and this,
That means there's something wrong.
Yes, that is correct.
and this is the lesson.
If you don't see it,